as I'm getting older, I can do different types of talks. So this will be more like a positioning type of talk, not so much on technical details, but I'll tell you a little bit about some technical things too. So it's kind of it's a grandiose title, but I'm going to try to convince you about one thing that I think it's happening in the wider computer science space, and try to convince you that there's a very, very interesting connection between the world of AI and the old world of simulation. So AI is everywhere. Everybody knows this, right? So why such a fast success? There's many reasons, but one reason that I think it's not usually, people don't think so much about it, is that the software stack that we use for building all these models is actually amazing, right? It's Python, so it's very easy to code. So I bet almost 90% of people here are coding in Python. They're not coding in C++, and they're not coding in Fortran, for sure, right? It's an open source environment in the sense that you actually have access to all these components. You can plug and play super easy. You can look at the code. Most of you have not paid a single cent for the software you're using, which, again, is amazing. You can use GPUs, right? It's pretty easy. You don't have to code a CUDA. You just add a flag to TensorFlow or to PyTorch, and then suddenly you're just scaling to 4 GPUs, right? Again, amazing. And it's cloud ready. So most of the things that you do, you don't have to have your own hardware. You can just connect to the cloud and use it. So it's pretty amazing, and it's quite recent. And one of the reasons why we see that is because all this stack is being built mostly by a handful of players. So Google, Meta, Google has TensorFlow, Meta has PyTorch. There's been other sort of these frameworks, but the most widely used ones are driven by 2 companies. And that's actually pretty interesting because in a certain way that helps standardization. They set up the rules, they design TensorFlow, they design PyTorch. Everybody uses, everybody's more or less happy, so it's good. And again, because these are companies that are at their core software companies, or at least a big part of their business is related with software. These things like PyTorch and TensorFlow and all the even CUDA and all those layers that go all the way down to the hardware are pretty well designed. Python is sought for the programmer, right? Super easy to code. It's also something it's a language that is very easy to integrate with other ecosystems. You can, you go from using Python and databases to Python and visualization. You can do all that in Python, so it's pretty amazing. And if you think about it, you really don't have to think about how to connect the different layers of the stack. Everything just flows from top down. You code in Python, you're running on 100 machines on the cloud. Usually easy. It may be a little bit expensive, but it's easy, right? And this is cool. This is amazing. And it's also pretty recent in the computer science world or in engineering world, right? Maybe not all of you have been playing with computers for so long, but it was very hard to code anything and make it running on a different type of hardware. Like that was not something that was easy 10 years ago, even maybe 5 years ago. Now it's super, super easy. So before AI, becoming the cool thing, the thing that we all talk about, there were other things that were cool before this big AI era. And one of them was simulation, okay? When I was a computer science student, this was the cool thing. If you were able to do these sort of things, which combine physics and 3D, this was the cool thing. Okay, the people were doing AI. Maybe they were coding on these sort of Prolog-based type of system. Some people were doing neural networks that could have maybe 2 layers, and that was it for classification problems. So this was the cool thing, and we could actually do pretty interesting things in the simulation world. So simulation is actually a big, big, big thing. If we think about how we design objects, from bridges to chairs or tires, people will use simulation software. So it's been around for many, many decades, and it has a huge impact in the industry. People build things with that software. They build more than chatbots. They build bridges. They build buildings. They build actually things that exist in the real world, right? They use simulation to design drugs. So a lot of the drug design nowadays is not happening on the wet lab. So it's not happening with the liquids and the little things. It's actually designed on a computer. And then when you have a good candidate for a drug, you try to synthesize it. But most of the design is actually done using simulation software, not AI software yet, okay? But most of it is regular molecular dynamics simulation software. And even to understand the universe, so I've just read something about how people are using simulators to understand how the sun works and how black holes work. So simulation is a tool that's been used in science for many, many years. I like to call this real tech, a little bit mocking a little bit the AI craziness out there, because there's lots of technology it's in place, it's being used to solve real world problems. And in many cases, AI is kind of overpromised, right? We have a lot of technology there, but not so much actually solving real big world problems, right? So, but simulation software, and now I'm going to try to create this sort of opposition to the world of AI. So it's not a recent trend. I'm old, and this was cool back then, so it's not recent. It's also not a trend led by just a couple of players or just a few players, right? There's a few companies developing simulation software, but none of them is kind of as big and as dominating as Google or Meta or other companies like that you guys know. Obviously, that's in some cases a good thing, some cases not a good thing. So for example, there's not a unifying technology like TensorFlow or PyTorch for simulation. People code in C++, people code in C, in Fortran, in lots of languages. There's no standard for data, there's no standard for visualization. There's thousands of tools for visualizations. It's just a mess. And actually most of the business, it's these big companies that do simulation, let's say for auto industry and all that, they develop software not on a closed source strategy. Like you buy the software and you cannot connect it very easily with other softwares. You get what's called a vendor lock-in. Like you bought that software, you're done. You have to buy that software for the next 20 years. So, and it's not API centric. We sometimes forget this, right? When we think about building things in AI, we already think about those systems from the point of view of an API. Other people will be able to call whatever we're building, or we can use some software that's out there in a server and we can just call the API. Or even if we have to install something locally, there's a clean API. That's, again, relatively recent. We're exposing software in a way that other coders can use, not other operators can use. So we don't need UIs, user interfaces, for building AI systems. We don't do that, right? We just use command line, right? So, but there's also other differences in the simulation world. So one of the differences is that it's very, very difficult to run things at scale. And the way people have been doing that in the last decades is using supercomputers. So you've probably heard the acronym HPC, so high performance computing. And that basically means a room like this full of usually CPUs connected by some fast network technology. Not so much like the, let's say, rack with 4 GPUs that we're used in the AI world. So it's pretty hard, it's pretty expensive to scale things. And tooling in general, it's really not as nice. So there's not weight-in biases for simulation. There's not any array from any scale that allows you to scale things on the cloud. There's none of that. Or there are a few systems, but they're very, very complicated. And usually kind of very old school. So it's here, right? But there is another fundamental difference, and I think connects a little bit with what Miguel Manel is saying. So it's simulation in general. When we think about simulation of things in the physical world, it's not data-driven, right? So AI is data-driven. We have data. We learn from data. In this case, people actually did, modeling, and they came up with some equations, usually partial differential equations, that relate how quantities change in the world, right? So if I drop this object here, it will fall on the ground with a certain speed and it would take some time, and we know that. We don't have to learn that from data. We know that, right? We could learn from data. I could be just throwing objects and timing it. Not this one. I won't do that. But it's possible. But in this case, we actually know the rules. We know how things work, right? And because of that, we build programs that work in a different way. They can be considered mechanistic, right? We actually say, okay, take this value, apply this equation here, add whatever, and then come up with a result and solve it with this algorithm. So we do have a mechanistic way of computing. So this is kind of what I want to convince you, is that when we think about computation, if we just kind of scope out and stop talking about AI and other techniques, and we just think about solving problems with computers, then we actually have a much bigger landscape, and that landscape has at least two ends. So I'm going to say on this end here is the setup. Let me move out. It's the data-driven methods that probably we've been talking here in this room for some hours. They're very flexible models itself. Like the modeling is very flexible. We use things like deep neural networks. There are some components in this technology that are really, really cool. One of them is differentiability, right? You write code which, neural networks and the code you write, you can take derivatives, and that's pretty cool, right? So that's why you can train objects, you can train models. And we typically apply these sort of models in domains in which we don't know the rules, or the rules are so complex that we cannot quickly describe them, right? So for example, natural language processing. There are some rules. There's grammar and there's syntax, but the generative rules are very, very complicated and they're not rich enough. So we need to learn it from data, and we do that. That's why we have these amazing models. So large language models are models that allow us to operate in this domain for which we really don't have rules, right? Or vision, right? Machine vision. Like, how do you write a piece of code that reads a landscape? Like you have to learn it. It's very easy. It's very difficult to actually write the rules, right? So when rules are very, very difficult to write, we've been developing these models that learn from data, and they seem to be pretty cool. And on the other spectrum, we are in the world where we know how things work. People have spent decades, centuries figuring those things out, so we know the rules, right? So in that case, we usually have models which are very specialized. For example, models that explain how a flow of air goes into a tube and what happens inside, and we can have wind tunnels and we have wind turbines and things like that. So we know the rules, and we basically build programs that execute those rules. So that's it, right? So this is a spectrum. So the question is, what's in the middle, right? If we have two ends of the spectrum, what's in the middle, right? And this is what I think is pretty cool, and it's happening in the last, let's say, 5 years. A lot of things are happening in the middle. So there's two possible directions. So we can either, let me go back, go to that side and say, okay, I'm going to build things on that side, but I'm going to use the technology from this side. I'm going to use neural networks and differentiable components to do those things. Or you can go to this side and say, I'm going to solve problems from this side using these tools, but problems that have to do with, let's say, simulating wind flows. Okay, so you can go both ways. So one of the ways is actually, okay, I love neural networks. They're super flexible, so I'm going to start solving physics problems with neural networks. How can we do that? Well, we know that this side here is data-driven, so I can, for example, just generate data. I can use the simulators that I have to generate data. And I think there's been a few talks about synthetic data. So I can just use the simulator, let's say a simulator that controls how objects react to flows in a wind tunnel. And I can just generate tons and tons of these simulations, which sometimes take hours, and build a large data set of objects inside the wind tunnel. And then use a neural network to learn to predict what's going to happen if I change the object, let's say an F1 car, by an helicopter, and see what happens, right? You can just plug and play different objects there. Or, as I was telling you, you can use the technologies that we have for neural networks to actually write mechanistic software. So let's go a little bit one step down this stack, and there's I'm going to tell you about three things. I'm going to go very quickly over them, so I'm not going to go in detail, but I would like you guys to kind of remember these three things. So one is just using machine learning to learn how to simulate the things that we do with regular classic simulators. The second one is to use machine learning to optimize how these classical objects, this classical software operates. And the third one, which is the coolest one, is how do you look at all this as coding and use very sophisticated tools that we now have from the neural network world to just code everything and just think about everything as a neural network. So let's talk first about machine learning-based simulators. Here, it's basically learning how to simulate, having a neural network that predicts the result of a simulation by observing reality. We do actually have data sets out there of real data. We're collecting data from mountains and knowing how the wind flows in between the mountains. We have that data. It's usually not a lot of data, but we can also just generate as much data as we want, using classical simulators. So we actually build a simulation using classical software. We run that simulation thousands of times on computers in parallel. That's fine. We just use the vast amounts of compute that we have in the cloud, and we generate a huge data set of synthetic data. We mix both. We have synthetic data, we have the real data, and we basically take a neural network to learn from all that data to predict whatever we want in the physical world. So there's lots of advantages here. One of them is that neural networks are usually much faster than simulators. And usually we don't have enough real-world data to actually just train a classifier or train a predictor with just real-world data. That almost never happens. So here's one example. So this is an object placed on a wind tunnel, and you see there, what you see there are pressures. So this is basically where you get the resistance, right? So what you see on one side is a object, it's a random object, placed on a wind tunnel, and then you simulate the wind tunnel. It takes hours to run that simulation. Well, it depends on the object, but it can take up to hours. And then you have the same object and the quantities, in this case, the pressure, being predicted using a graph neural network. And the error is relatively small, but what's important here is that side, the neural network, is about 40,000 times faster than the classical simulator. So if you're just trying things and testing things before you want a high-resolution simulation, this is the way to go. So this is one way of doing it. And this works. So the option number 2 is to use machine learning to optimize the simulators. So simulators are complex pieces of software. You usually describe whatever you want to simulate in a file, and then you run the simulator, but then you have like 20 parameters or hyperparameters you can play with. And these have huge impact. Like, for example, they have to do with the stability of the solution, whether or not this is going to take 2 days or 2 hours. So there's lots of these parameters that are important, but they're very difficult to set. So here's another way, and what people are doing and what we're doing is we're just using a simulator. We kind of play randomly with the parameters, so we have some smarter way of doing that. But we can generate a data set that says, for these parameters, right, if I change the time step or if I change the resolution from value A to value B, this is what happens in the end. It took 2 hours to simulate, and the result is stable or isn't stable. So you basically can also build data sets with all this data, and then learn from this data, this big data set, to predict what happens when you change some hyperparameters in the simulation before you run the simulation. And again, simulations sometimes take hours, so when you want to save compute time, this is another way of doing it. So let me finish just by telling you about differentiable simulation, which is the coolest thing now, at least in this world between machine learning and simulation. And this has to do with differentiable programming, which is basically what all of you are doing, which is it's building a program that allows you to take derivatives of the inputs with respect to the outputs and the way around. So you can basically place that program in an optimization loop, which is a neural network, right? So whenever you're coding with these languages, TensorFlow, PyTorch, Keras, Theano, JAX, LangChain, and there's a few others, if you code something on these languages, then the program is differentiable, meaning that you can actually take derivatives of the functions that you write. And that's why you can put them in an optimization framework, right? So when you do that, this is great. So you basically can do something which is, okay, so now I'm going to use these languages to write my old software. Instead of being written in Fortran or in C++, I'm going to use JAX, Python JAX, to build a simulation software as we have for 20 years. So this is pretty cool because if you do that, then you have the forward pass, which is mechanistic computation, which is it's computing whatever you need for the wind tunnel or for the molecules or whatever physical domain you're working with. But then you can do the backprop. So you can actually take this piece of software, and if you have a neural network that does something, you can put the neural network behind it or after it, and you can train everything together. But here's the difference, and this is why this is so cool, is that usually when we're doing, working with neural networks, they have this problem. They don't have enough bias, right? They can model anything. The model is so flexible that they don't know about physics. They don't know about math. They don't know about the real world. But if you can code something which is still differentiable, and it has the rules of physics in it, because you know the relations between the inputs and the outputs, then you basically expand the neural network with the knowledge of the world and the physical knowledge that we actually have, and the network can only learn in a way that, in a certain way, respects the physics, right? So just to finish off, this is getting a little bit longer than I expected. Just think about not neural networks and TensorFlow. Think about, or PyTorch, or whatever language you're using. Think about, okay, neural networks are just the first version of all software that we can build using differentiable programming. So everything in a certain way is not a neural network, but it's optimizable. And neural networks are just one part of the things we can do with these sort of languages. So to finish, there's lots of things happening in these two worlds. So there are not actually two different worlds. They're just one big world, which up until now has been sort of separated in two parts. And what we're seeing and we're so super excited about is what's happening in between, which is a convergence of these techniques to allow us to do better science and better engineering using the tools that we are now using for neural networks. Thank you.
Thank you very much, Luis. We actually have one question. If someone wants to drop other questions, please go ahead. I will start for the first one. In a simulator, normally the hyperparameters are constrained by the model object being simulated. So how will the AI set the react to these constraints of the hyperparameters of the model?
Do you mind repeating the question?
So in a simulator, the hyperparameters constraint of the model based, yeah. How the AI will deal with that, or it reacts to these constraints?
So I think there's two ways of looking at this question. So when I'm talking about hyperparameters in a simulator, those are things like, for example, what is the definition of the time step? Am I simulating something every second? Am I doing the computation for every second, or for every millisecond, or for every nanosecond? That's one of the hyperparameters in a simulator, right? It's not like the hyperparameters that we have on models, which are usually kind of number of layers and everything that you want to do with your model. In simulation, a hyperparameter is how am I going to run this algorithm? So things like resolution, time resolution, number of iterations, and all that. And those are super in very much the same way that it's difficult to set those on AI models, on machine learning models. It's also very difficult to do that on the simulation world. So learning those and optimizing those is key for running simulation at scale, and you can do that with neural networks.
So we have now people are starting writing their questions, so I'm trying just to get a sense of them. So actually there was a question that pops up before. So would it be possible to completely stop using animal models using these techniques? I believe animal experiences using these techniques.
So which type of models, I'm sorry?
Using animal models, but I will say that it is animal test subject to
animal models.
Yeah, animal models. I don't know.
So again, let me look at.
They are popping up.
Oh, no, they're popping up. Animal models. Yes. So if you have a simulator for an animal, and there's simulators, for example, I mean, it depends on what you're simulating. But for example, one of the simulators that is out there, which is pretty cool, is a biomechanical simulator, right? So, it simulates how your leg bends and, like the pressure on your bones. So there's simulators for that. We know the physics, right? So you can use that. You can recode those, or you can use those either to generate data to then train a neural network, or if you really are into it, you can code the whole thing using one. So you rebuild the simulator, use the same equations, but you write the simulator using something like JAX, and then your simulator is a neural network. Or again, both neural networks and your simulator become a component, but can become differentiable components, or are differentiable components, so you can play them. Just plug and play. You can do back propagation on that.
Great. A little bit different from the start of your presentation. What do you believe is needed for the market to change from a closed source approach to open source?
So what is the
I believe
in general?
Is in general the question of open source that is nowadays enabling so much of these developments.
So I think we can think about open source as a form of democracy, because it really helps people come into the business, right? Just think about what would AI be if we didn't have things like TensorFlow or PyTorch. Probably only a few of us would be actually coding something in C++ from the basics and still have the performance that we need. So it's great, and I think for a country like us, for Portugal, it's amazing because it actually puts us more or less in the same level as other countries that have a lot more resources. So I'm a big believer on open source, and all our code actually is open source at Inductiva.
Yeah.
Almost all, 95%.
95%. We don't have anything next, so if you want to keep just for continuing these questions
I'm okay.
here,
I'm not sure if they're bored, but
so just a couple of two others. What are the limits of the physics that can be coded in differential programming way? And what are your thoughts on that?
So so we've seen this in a few fields. So one of the fields that it's very promising is molecular dynamics. So molecular dynamics is basically when you code something that it's an n-body problem. So you have an atom, and then you have another atom, and you want to see how these interact. But when you have lots of them, they become, the system becomes super, super complicated, so it's unstable and you want to simulate. But basically what you usually want to do when you're doing drug design is you want to know if when a protein or when a compound and a protein interact, does the compound do something around the protein? Like, for example, covering a part and sticking to that part, right? So that's what drug design is mostly about. Like, you want to get something that glues to something else. And you have to compute lots of these physical forces to make sure that happens and it's stable and all that. So what you want to do sometimes is, once you reach an equilibrium, you want to do small variations, so to see what are the different things that would do the same, right? And in that case, again, what you want to be able to do is to optimize. So if your algorithm respects the physics and at the same time you're doing an optimization loop so that the changes that happen in your model still respect the physics, then you basically have a single technology to both the forward pass, which we can always do, and then the backward pass. So explore the space. So this is a place where we're seeing a lot of traction. Also, everything has to do with 3D in general. Graphical networks, for example, but everything we have, it has to do with 3D, with the real world, is having a lot of traction. So design of shapes of objects, for example, you want to optimize the shape of this object. Again, if you can code the entire physical system with this differentiable programming, basically what you get is something that allows you to test variations and morph the shape of this object, because you're in an optimization loop, right? So,
I will put a personal question. I came from this side of the
that side.
That side
so did
of
I.
the physics. I'm a geophysicist by background, and then I moved, and I'm a big passion of ML too, and the benefits of it. But actually, it's quite of a concern. We are getting into a world of a lot of what we produce is going to really deep neural networks and all the LLMs and everything that is starting to be the sense that I have is starting to be more and more black box. And many times we're discussing explainability, as we saw here before, in different types of technologies. And for a guy that comes from the physics world, I have a concern that how are we going to progress the physics when we have that much availability on stochastic principles that are based on these neural networks and that are difficult to explain? What are your thoughts on that? Did something that you feel that could be sensitive for the future, the improvements on the physics, since we have the machines that help us that much, or it should not be a constraint?
So it's interesting that we're talking about things like interpretability, right? And it's very difficult to interpret a black box like a neural network. Obviously, there's principles, and we kind of know some of the things that are happening there. But the basic problem is that usually neural networks are very flexible models, meaning that they don't have bias. They're not, it's difficult to code the bias on a deep learning model. So because it's so difficult, then you don't have a way of interpreting because the space of learnable models is huge, right? But as I was trying to explain, if you use the same set of technologies, but you actually build modules that are mechanistic, that they actually respect the laws of physics, right? We know that when this happens, if this goes up, this has to go down, right? Yeah. This is one of the core things, like conservation of something in physics, right? This happens all the time, right? So things like that, or relations that have to do with how things propagate, the maximum speed that they can propagate, all that can be placed in these modules, all that information, and you can connect that to a neural network, either as a loss function, so it makes sure that you're respecting the physics, or when you're transferring from one layer to the other, you make sure that the relations between the things have to respect that physical law. So in a certain way, the fact that we're now picking up these technologies from neural networks and applying them to other fields, I think it's the way to go in terms of interpretability, because then you get interpretability by design.
By design.